Sorry. I'm in trouble. Good afternoon.
Hey,
How's everything going today?
going fine.
Good. Well, let's see if Christina shows up. I mean, not Christina, Kenya. Sorry. Christina's in the other class. And we'll wait for a minute. It's having a hard time getting connected today. Did you have a hard time too? Or no?
What?
Did you have a hard time connecting today?
No.
Good. All right, so the next thing to look at is acid and bases, right? And that's it.
Yes.
It's not
We
much.
looked at some of it today.
Yeah.
Yesterday.
Yeah, we
I mean,
looked at
Wednesday.
we looked at the definitions of the three definitions, right?
Yes, it was the 3 definitions.
Okay, yeah, now we're gonna apply them. Because that's the main thing is why do we want the definitions, right?
Yeah.
We need them for a reason.
Also, I think I have like 6 assignments turned in. I can't remember how
Okay,
many I have
cool.
turned in.
I haven't graded anything. I've been so darn busy.
That have,
Everything in my school.
yeah, they haven't been great.
No, nothing's been graded for a while. So I need to start grading stuff. That's my other thing. And I've got to have time for all that. And I don't. There's only 24 hours a day.
Yeah, that's true.
Unfortunately. Wish there were more. All right, well, I don't see her yet. So let me just go ahead and click on the student acids basis. Well, actually, here's the introduction. So that basically kind of tells you what we're covering. If it ever comes. See how it's going slow? So I'm having a hard time today with the internet. Just not even loading. What if I have to reload again? No, it's fine. It's just going slow, that's all. Can't even click on that. It won't come up. There we go. We were just talking about the introduction to acids and bases and what we were looking at. Okay, so these are your objectives and your overview right here. So we'll learn about acids, bases, determine pH of a solution based on the concentration of hydrogen atoms and determine whether an acid or base is strong or weak. Understand the pH scale and learn about the amphoteric nature of water and what buffering is and titration, neutralization reactions. That's basically it. Okay, so don't worry about the reading. I need to erase all that. This was kind of from my other class. So it came in with the reading and I didn't realize it had the reading on it. So never mind. All right, don't look at the reading. All right, so we're looking at acids and bases. And we already went through the 3 types of definitions, and they're important because conjugate acid, conjugate base, we're going to get a little practice on that again, just to get you back in the loop, in case you've forgotten. So I'm going to go ahead and do the student acids and bases PowerPoint. If it ever loads, because it's taking forever lately. Come on. Yeah. So it must be my internet. But it doesn't look like it's my internet. It looks pretty sturdy. See? Nothing wrong with it. Okay. Come on, acids and bases. Wake up. Gosh. Let me see if I have it in my other place, because this is just taking way too long. Recent. If I go to here, not there, here, I should have it in recent because I just accessed not that long ago. See, it says it can't be reached. So let me see. Quick access. I got way too much stuff over here. Yeah. Assignment. That's not your assignment. That's an assignment for the other class. Okay. Oh, come on. Just not doing it. See, it's just not doing it, period. Downloads. Maybe under downloads. It'll be there. If you see it, yell. Students, acids and bases, I don't see it. Nope. Darn it. Just not. There's too many things on the downloads. There's no way I'll find it unless I look for it. Titration lake, lab, protein, amino acid, acids. That's acids. That's not acids and bases. Students, acids and bases. Mass efficient learning. See, I don't see it. Oh, darn it. Okay. Apparently the stuff is just not wanting to. There we go. Haha, found it. All right, so we're gonna go back over it. More apps. No, more apps than that. Where in the heck is my, yeah, where is my, You're so annoying. This one. Okay, there we go. Maybe now it'll come up. There it is. Boom, boom. All right, there we go. All right, so we looked at, like I said, all the definitions just to get started. That was, and did we actually go through the definitions or did we just look at the common ones? Anyway, just to recap.
I think we.
Huh?
We went through
Okay.
definition. We went through
Okay. Well, we're going to go ahead and go through them one little time more. Okay, just so you know, the definition of an Arrhenius acid is one that produces hydrogen ions, and a base produces hydroxide ions. Problem is some bases don't have hydroxide ions, but it's okay, because if you put it in water, then it can produce OHs. So acid-base definitions for Braun-Stellari is acids are a proton donor and bases are proton acceptor. Here's where you look for the acid-base conjugate pairs, right? So this is the base, this is the acid. So the ammonia conjugate pair is the conjugate base. So the ammonia and the hydroxide are the hydroxide ion are the conjugate base pair, and the conjugate acid base are water and ammonium ion. Okay. I did it backwards. I just realized I said it backwards. I meant to say water and hydroxide ion are the acid conjugate base. And the ones that are in the right color, see, that's the thing. It's just they're both acids. That's why it drew me to it. but actually the base, conjugate base are, base and conjugate acid are the ammonia and ammonium. And the acid and the OH are the conjugate acid base pair. All right, so once you look at that, we have the last definition, which is the, oh, I think I passed it, didn't I? There it is. The Lewis acid base definitions is, one of them is an electron pair acceptor, and that would be the acid. And the base is an electron pair donor. All right, so, okay, now with that in mind, let's look at the pH scale. All right, so a pH scale is for acids and bases, whichever definition it is, it doesn't matter. But 7 is neutral, right? And we know that pure water is neutral. Now, if you have water that has chemicals in it, or you have water that has minerals in it, or whatever, then you're going to have a slightly higher or lower depending on what's in it, pH. But pure water, distilled water, is 10 to the negative 7 for the hydroxide ions, hydrogen ion concentration, and 7 for the pH. I don't know if you noticed, but the pH, if there's nothing in front of it, is exactly the same. So the hydronium ion concentration is 10 to negative 14, pH is 14. Hydronium ion concentration here is 10 to negative 13, pH is 13, and so on and so forth, all the way down to 10 to the 0. And the pH here would be 0. Okay. All right, so let's look at, well, these are some substances that you know. So sodium hydroxide is also known as lye, and this is 1 molar sodium hydroxide. So the pH is very low, right? I mean, low as in low concentration of hydrogen ions, but the pH is high because the number is actually the negative 14. So ammonia, which is a cleaner that you use in your house, is 2 magnitudes away from that of lye. So 2 magnitudes would be 100 times lower, right? And then you've got your blood, which is between 7.35 and 7.45. So you could say 7.4 is the normal. And that's quite a few magnitudes below that. And then you got pure water, which is 7. Milk, which is slightly basic. Acidic. I said basic, I'm sorry. Acidic. Vinegar, which is a little bit more acidic, is around 3. Lemon juice is a little bit less than 3, like about 2.5 maybe. Stomach acid is 2, and 1 molar hydrochloric acid, which is the same acid as the stomach acid. But the stomach acid here is dilute. Here's a 1 molar concentration. And that's it. And then you've got another few. Vinegar again. Then you've got, and here they gave you the actual pH. 2.8 for this one, and 2.9 for soda, 3.8 for an orange. There it is, your blood again, 7.4, 11 for ammonia, and 11.7 for a vein cleaner. Right. So how do we?
I don't think your screen sharing.
Huh? I'm sorry. How do we calculate the pH? The pH we calculate it by taking the negative log of the concentration of hydrogen ions. So let's say that your pH was 10, right? Then the negative log of 1 times 10
Yeah,
negative 10. 10. All right. But if you have a number like 1.8 times 10 to negative 5, then you actually have to do the log. So in order to do that, you hit your negative key first, right? And then you put the log button. And then it gives you log in parentheses. And then you put the number, which is 1.8, and it's 10 to the negative 5. So second double E, that is exponent. That's what that means. And then negative 5, and use the negative, that is the negative, not the minus. Otherwise, it'll give you an error. And that gives me 4.74. Now, since we said it was negative log, right? The negative becomes positive. You see that? All right. And that's it. And that's how we deal with this one. Yeah. If you have the opposite, if you have pH and you want to know the concentration, what you need to do is elevate it to the pH power, whatever the pH may be. All right, so let's look at these and let's try them. Okay, so find the pH of a 0.15 molar solution. Okay, so for that one, once again, remember it's the negative log, right? So use negative and then use your log function and then 0.15 and then get the answer is 0.823. So the pH is very low. Oh, sorry. And then the other one, the pH of that one, it's going to be, that's the concentration, right? So you want a pH, you have to do the negative log. So negative log of 3.00 times, not times, sorry, second EE. Clear that. Second EE. I said delete. Okay, I'm going to put 3. Second EE negative 7. And that one is going to give you a close enough to negative 7, but with this in front, it's going to be a little bit lower, right? So it's going to be 6.522, which is what we need. 52 actually, because we have 3 sig here. So 6.52 times 10 to the negative 7, no, 6.52 period, right? All right, so now let's do this one. If the pH of Coke is 3.2, what is the hydrogen ion concentration? Like I said, this time you do second, and then you hit your log, and then you put the negative number, whatever that is, which in this case is 3.12, and you close the parentheses, and that will give you the concentration. And if you want it in scientific notation, you can just change it to psi by using the science engineering key, which is seconds SI-ENG, and then move it to psi and then hit enter. And that gives me a pH of 7.59 times 10 to the negative 4. So this is how you would do that, because pH is negative log of hydrogen ion concentration, then the negative pH is equal to the log of the hydrogen ion concentration. So, excuse me, if you take the anti-log or 10 to the x, right, of both sides, and you get that, then that is how you do this. And I got 7 point, they gave me 3 sig figs, so I was using 3, but 7.6 they say, but I have 7.59, which is nearly the same, right? 10 to negative 4. All right. And this tells you how to find the log, anti-log in your calculator. If you only, but only if you have a scientific one, okay? So it'll be the shift or second function and then the log button, okay? All right, so now we have this one, a solution of 8.5. What is the molarity of hydrogen ions in that solution? Right, so once again, you want the molarity, you have pH, so you need to 10 to the exit, right? So 10 to the negative 8.5. Second, 10 to the negative 8.5. And that gives me an answer of...
Not screen sharing.
Oh, I'm not? Oh, man. That's because I had to go find it somewhere. Forgot about that. Sorry. You should have said it sooner. And I would have realized I was really not screen sharing. All right, so sorry about that. There we go. There's my share. Now you can see what I was looking at, but here it is. All right, you can see that, right? Okay, so I get 3.16 times 10 to negative 9. Okay, now water, this is why we call it amphoteric. It's because it can function as an acid and base. Why? Because when it dissociates, it fulfills both definitions. It produces hydrogen ions and it produces hydroxide ions, because that is what water is. It's a hydrogen and a hydroxide ion together. And there's your Kw. So the Kw, and you notice here, like, look at hydronium ions. Hydronium ions and hydrogen ions are the same because the hydrogen hasn't got any electrons, so it's going to be extremely reactive, looking for an electron to
You're muted.
Okay, there we go. All right, so here we are. We have the picture, right, of the autoionization of water. And that's why it's known as an amphoteric substance, because it produces both requirements for acid and base. So if this is a neutral solution, then the concentration of hydronium ions and the concentration of hydroxide ions is going to be the same number, which is 1 times 10 to the negative 7. Therefore, water is an addition of the hydroxide ion concentration, and the hydronium ion concentration gives you 14. All right, so acid and bases are opposites, right? Then pH and pOH are also opposites. pOH doesn't really exist, but it is useful for doing the exchange between a base and an acid and having the pH instead of pOH. So pOH looks at the hydroxide ion concentration. And as you know, that is equal to 1 times 10 to the negative 14 anyway. So by subtracting the pH and pOH, which in this case would be 7 and 7, right? That gives you 14. Or if you had an acid, let's see, it was 3, then the pH would be 11, and so on and so forth. Okay, so this is an explanation, well, not an explanation, but a diagram of what's going on. So if your pH is basic, right, then your pOH is 0. So it's very high. If you're neutral, then everybody's 7. But if you're acidic, is the opposite. Your pH is 0, but your pOH is 14. All right, so when you calculate these, it's useful to know that the pH and pOH equal to 14, right? And you can find any of these answers like that. So here's the first one. The pOH, since it is hydroxide ion concentration, you got to pay attention to that. If they give you the hydroxide ion concentration, you're going to get a pOH. You're not going to get a pH. Then you have to get the pH, okay? So that means that the pH here is 11, right? All right, so let's do these problems. It says the pH of rainwater in a certain region of northwestern United States was 4.82. What is the hydrogen ion concentration of the rainwater? Okay, so this is just a normal one. So in order to get the hydrogen ion concentration, we have to elevate it to the power, right? So in this case, this is going to be a second anti-log, right, of negative 4.82. And that's going to give you the pH. pH is 1.51 times, no, sorry, the pH. I mean the concentration. 1.51 times 10 to the negative 5. And this diamond right here, you might want to take a picture of it, is very useful for converting. You get confused, you always look at this diamond, okay? All right, you know, you're taking a picture of it, or make sure you know which slide it is. It's slide 36 of these student acids and bases. So make sure you know that. All right, so here's the first problem. Let's remember this. A chemist dilutes concentrated hydrochloric acid to make two solutions, A and B. And we did these, didn't we? Yeah, we did do these because I remember putting them in a table. So we've already talked about this. We talked about what makes a strong acid strong and what makes a weak acid weak, right? That's what it is the amount of ionization. If it's fully ionized, then the acid is strong. If it's partially ionized, then the acid is weak. And here are some of the strong acids. So you've got nitric acid, hydrochloric acid, sulfuric acid, and perchloric acid. These are the four most well-known of the strong acids. Okay, since it is a strong acid, the reaction forward, in other words, towards the right, is favored, right? So you're definitely going to ionize completely. All right. And you have both in both. I mean, you have strong acids and strong bases, both, just like you have weak acids and weak bases. Okay, so the strong acid, nitric acid with water becomes hydroxide, sorry, not hydroxide, hydronium ion plus the nitrate. ion and is 100% dissociated in water, almost. Then you've got a weak acid, is much less than 100% ionized to water. And one of them would be acetic acid, which, as you know, that's vinegar. And there's a forward and a reverse reaction. You see that? You have both. When you have both, then you are not going to decide which way. So, of course, your concentration of hydroxide ions, hydronium ions, sorry, and acetate ions is going to be lower than if it was fully ionized, because some of them revert. Strong and weak acids. Okay, once again, the base that is strong is 100% dissociated in water, like sodium. Okay, but in water, they will join each other, right? And here you go. This is your reaction. So this time, the sodium and the hydroxide will open up. That's for a strong base. So there is no reverting. Another strong base would be potassium hydroxide and calcium hydroxide and calcium oxide, which is lime. Okay, now, next one is the weak bases. They are the same as the acid, less than 100% ionized. And so the forward reaction is not favored here. That actually depends on your acid and your base, which one's more favored than the other, but they're not 100% favored. So ammonia is one of them. So ammonia would get with water, and water will produce the ammonium ion and the hydroxide ion. And this right here is important that you know how to do the conjugate acid base pairs, so that you are able to write what is known as a constant, right? So the Ka or Kb, in this case would be the Kb because it's a base. And here's some of the more famous ones. You got benzoate ion, which is in Coca-Cola. You've got the phosphate ion, which is in Miracle-Gro, ammonia, and caffeine. Okay, so this is what I was telling you. Ka, Kb. So the Ka of any acid is going to have its own Ka at a certain temperature, usually at 25 Celsius. And it's going to be the dissociated ions concentration over the undissociated ion. I mean, not ion, but compound concentration. So that's going to equal to whatever the Ka, which is a constant that you have to look up, because each, like I said, each one has a different one. So we cannot say, oh, it's always going to be 1.8 times 10 to the negative 5. No, it's not. As a matter of fact, right here is a list of a bunch of them, not all of them. And here it's showing you the acid and the base, the conjugate base. The acid, so the rule is that if you have a strong acid, you're going to have a weak conjugate base. If you have a weak acid, then you're going to have a strong conjugate base. Okay. All right. So in order to write it, like I said, you have to write it like that. Now, this, in order to solve for it, and the same thing with the base, okay? One of the things you need to remember is that if you want to calculate it, any of the concentrations, like that you're given one, and you have to figure out, I mean, you're given all the others and you have to figure out one of them, then you need to do the what is known as the ICE table. And this is a quadratic equation normally, but you can do the ICE table and assume some things for weak acids only though. So the initial, right, we say that at the beginning, everything was 100% the acetic acid, and there was no hydroxide ion, I mean, no hydronium or acetate ions. The change would be negative X, and the other ones would be plus X and X, because this one's decreasing and these two are increasing. And the equilibrium is going to be that minus that, right? And that minus that. So that just kind of gives, I mean, not minus, but it just gives you the same number. So it's an X. All right, once you do that, then you can now write your equation using that. So obviously the top is X times X is X squared, right? Divided by 1 minus X. So that is a quadratic equation. Do you all remember the formula for a quadratic equation? I always forget this one. I know it's A, B. Oh, Lord, I've forgotten how it is. I haven't used it in a while because we don't really use it that much in chemistry because we have a solution that it makes it easy, which is an approximation, which is very close, by the way. If you have a less than 10 to negative 5, you see that? Or smaller, right? All right, so here we go. This one is the I lost me for a minute there. Okay, so here we go. The equilibrium.
I think you're muted again.
There we go. It muted me again. I think it's because my interstate's a little unstable. So it keeps muting me every time it goes out. And then I don't realize it's muted me until you say something. Then I can hear you. And I said, oh, that must be why.
Yeah, screen
Yeah.
recording either.
Yeah, it keeps doing that to me today. Anyway, remember, it's done it before. Okay, so we had the, oops, let's see. Yeah, we had that. Yeah, okay, so there's the ICE table for a base. I mean, for an acid, sorry. For a base is a little different. So like I said, you can assume it's small and do this. So X squared divided by 1, right? Because X minus 1, and if that X is really small, then it's not going to be that important. So you can just use this. And then now you can see an easy solution, right? So you just take the square root of 1.8 times 10 to the negative 5 to figure out what x is. And the answer is 4.2 times 10 to the negative 3. And that pH gives us 2.37. That is if you did it that way. If you actually calculated it, look how close it is. So it's pretty close, right? I mean, it's not that super close, but it saves a lot of work. Okay, so for a base, you have to do the base a little different. Instead of having it as 1, right? You have it as 0.00010. So the same thing, the initial change, same thing. Everything's the same, except for that one thing, right? Okay, so that when you're solving it, it's still x squared, but it's 0.010 minus x. And that's the one you neglect, right? So once you do the non-quadratic equation, then it works just fine too. Right. So let's say you have that. So the very first thing they're asking you is calculate the pH. So very first thing that you need to know is which one of these, you're going to have to, you have the concentration of the ammonia. And ammonia is going to be the concentration of OHs and NH4. So you set up your KB, which is equal to x squared over 0.01 minus x, right? Once you solve for it, once you get all your numbers first, though, then you get your answer. The pH is 10.63. In this case, you didn't need to do any of that crazy stuff because it was right there. But the KB, if they asked you to calculate with the KB, then you would need to. All right, don't forget that the litmus paper is turned, if it's blue litmus paper, it's turned red by an acid, and the red litmus paper is turned blue by a base. And there are other ways of measuring, and those are the multicolored, the universal indicators, which are also multicolored. And then you've got a pH meter, which is just an apparatus that measures the concentration of hydrogen ions. And then you have the indicators, which are not universal, but they are specific indicators for either acid or base. And one of them is phenolphthalein. And the natural indicators like red cabbage or radish will do that. And if you're doing a paper test, what you do is you check. If all you want to know is qualitative, not quantitative, right? You just want to know if it's an acid or base, then you stick this red paper or the blue paper into it. And if it changes, then you've got whatever you were looking for. If not, then you don't. All right. And then you also could do the pH paper, but in that case, you would want to know the range at least. And then, of course, you have the accurate measure of a pH meter. And salts are what is formed when you have a reaction of an acid and a base together. You form a salt and water. Okay, so this is why we need to know that. Okay, when we are doing reactions, which are called neutralization reactions, you usually will have an acid and a base, and you will generate water, and you will form a salt. What is a salt? A salt, all it is a metal and a non-metal, or a metal and a polyatomic ion. That's salt. So in this case, it would be sodium citrate, right? That would be, sodium, that's not citrate. What is that? That's oxalate, sodium oxalate. and what? Okay. And you can set up the titration apparatus. It tells you how here. You are probably having to do that in the lab. Don't forget you have lab activities too, along with this. Do not forget to do those. They are also going to be due, and they're 25% of this grade. So make sure that you have them, okay? Because the lecture is 3 points and your lab is 1, so that's why it's 25%, right? So 1/4. All right. So these are your steps when you do the titration. You add the solution from the burette. Depending on which one you're titrating, if you're titrating an acid, then you use a base. If you're titrating a base, then you use an acid. And then you use an indicator, usually phenolphthalein, because it is very specific as to a base or an acid. One is colorless, the other one's pink. And that is called neutralization. Once you have your reaction happening, the acid has been neutralized. That's why antacids are bases. Okay, so let's say you're standardizing a solution of sodium hydroxide. You want to determine the concentration. Okay, so I'm going to go through the entire calculations because you really need to know. Hold on, I need my tools, which they're not there. I don't know why they're not there, but they're not. Where are my tools? This is weird. Huh. Weird. Let me share my screen again. There they are. There's my tools. I guess I wasn't sharing. Oh man, I wish I'd have known that. Okay, so I'm going to do some annotations, some actual drawings here. All right, let me go ahead and pick it up and find it for you. All right, so this is how you do this. It's kind of simple, but it is a step-by-step procedure. So the very first thing is to know the numbers, right? And we have the numbers here. Come on, there they are. Okay, so the very first thing to do is to figure out how many moles you have in here. Okay, sorry, in here, in the HCl, because we know how much we used and what the concentration is. So we need to know how many moles. All right, the very first thing is to find, remember, molarity is equal to moles of the solute per liter of the solution. Okay, so we have the volume, right, which is the liters, which all we need to do is calculate that. I mean, convert that into liters. So it's 252 liters. And the moles we do not know, but we do know the molarity, and the molarity is right here, right? So then that is going to be equal to the molarity, which is 0.0998 molar, which remember that is moles per liter, right? Times, now we're going to multiply it times the liters, which we got 0.225. No, 252, sorry, 252. All right, and liters will cancel and you have moles. So when you multiply this, you're going to get the number of moles that you have. Okay, so the answer here is 0.0998 times 0.252, right? And that get 0.0252, oops. 0.0252. Okay, just realized that I don't have the 0 on there. Okay, the answer is going to be 2.5 times 10 to the third. Let's see how many sig figs. We have 3. 2.51 times 10 to the third moles of HCl. Okay, now we know that by the equation that we know it is HCl plus NaOH, and we have to balance it if it needs to be balanced. That's going to give us water, remember, and a salt. And the salt in this case is sodium chloride, so salt. The funny thing is the salt is salt in this case, what we call salt. All right, so it is balanced. And as you can see, for every one of these, we have one of those. So the answer is we have this many moles, right, of hydrochloric acid, which is same thing as the number of moles of sodium hydroxide. So all we now need to do is divide it by the number that they said they used. And in that case, that would be 2.51 times 10 to the third moles over liter, right? So the liter is 0.03562 liters. And that's how you know how to calculate how much it took to actually what the molarity. I mean, if you know the number of moles, you can calculate those. Then you can actually divide it by the number that they gave you, they used, and you can get the concentration, and very accurately, by the way. So it's 2.51 second EE to the -3 divided by 0.03562. And the answer for that is 7.05 times 10 to the -2 molar sodium hydroxide. I know this is getting a little too much in here, but there's your answer. So I'm going to circle it for you. So there are your two answers. First, you needed to figure out the number of moles, 1, and then you needed to figure the number of moles to figure the molarity. And that's how you do it. So that's how you figure out how much the concentration of an unknown acid or a base by titration. This is how it works. Okay. All right, so let's see, clear that. Now that's a big mess there, but when you see the recorded lecture, hopefully it'll make more sense since you'll see it written step by step. All right, so next thing we need to do is to see if we can do a problem ourselves. Okay. All right. So one of the things that you also need to know how to do is how to dilute something. So if they're telling you that you have 50 milliliters, okay, so you want to make, you have to make 0.5 molar sodium hydroxide, but you don't know how, okay, but you only have 50 milliliters of 3 molar. So how much water do you need to add, right? Okay, so this is the same as obviously you're diluting it, but the formula is M1 V1 equal M2 V2. So in this case, you have M1 but you do not have the V2, right? This is what you're solving for. So V2 will be equal to M1 over times V1 over M2. So in this case, M1 being the molarity that you're starting with, which is 3 moles, 2 molar. And this time you don't have to change it to liters because they gave it to you in milliliters. So your answer is going to be in milliliters. If you want it in liters, then they will tell you that. Okay. And you're dividing it by the molarity of the other one. So 0.50 molar. And that's going to give you the amount of volume. So when you multiply 3 times 50 and divide it by 0.5, you're going to get a number which is 300, right? So 300 milliliters is how much you need to add to the 50. So it's 300 milliliters of water for 50 milliliters of that 3 molar sodium hydroxide. And it gives you the answer, which is 350 milliliters of the 0.5 molar sodium hydroxide. See? So that's how you would do that. So let's look at it. A lot of times in the lab, you are going to have a stock solution and you're going to have to dilute. So the best thing to do is to know how. So this is how you do it. And see, when you don't know how much water to add, you do this concentration. Oh, sorry. I said 300. No, it actually needs to go up to 300. So you need to do 250. Yeah, I forgot to subtract. All right, so another one. This is it right here. Oh, let's do that one. Okay, you have a stock bottle of hydrochloric acid, which is 12.1. So that is molarity 1. Oh, sorry, let me do this. That is molarity 1, right? It's equal 12.1 molar. Volume 1 is equal, we do not know, right? Molarity 2 is equal to 0.10 molar. And we volume 2, we need 400, right? So we do not know how much to add of this. This is the question. All right, so V1 is going to be equal to M2 V2 over M1, right? So V1 is equal to 0.10 molar times 400 milliliters divided by V2, which is 12.1 molar. So V1 is equal to, let's see, clear. So 0.10 times 400 divided by 12.1. The answer is 3.3 milliliters. So you want to use 3.3 milliliters of this into 400 milliliters of water. So how much water? So it's 3.3 milliliters of 12.1 molar, right? And then HCl, oops, HCl, and then you're adding the water, which is 400, right? So 400 minus 3.3, it's going to give you 396.7. So 396.7 milliliters of H2O. And that's how you dilute it. Or you can just say, I put 3.3 milliliters and bring the volume up to 400, which is one way of doing it also. Okay. And that's that. That is all that we needed to do today. And we are done with acids and bases. So next time what we'll be doing is actually reviewing. Let me show you something before you go. Okay, that I need to unshare this. Actually, no, I don't need to unshare, but I do need to make this smaller so I can get out of here. It's not letting me. No, because I have, there we go. Now I will. Come on. There we go. All right, so for this, I want you to see, let's see here. Yeah, okay. I'm going back to modules. Since we are done, the final exam modules right here. Oh, come on, go slow. I go fast, I know. All right, there we go. So this is your final exam. I'm going to be adding over here. Wait, no, that's not it. Ah, there we go. Sorry, I already added it. The final exam review. Which you need to download or at least have handy next class period. And we're going to start it. We're not going to finish it. Come on, let's go. It's waiting. It's very unstable for me too and for you guys. Someday, there it goes. Okay. So this, come on. Yeah, this right here, I'm going to fill about half of it. I'm going to post a second one. If you complete that one, then you will have bonus points towards your final, okay? So this one and the other one together are going to be 25 points. So if you complete the half that I don't complete on this one, right? Which is probably a little more than half or maybe less, I don't know. Then see, there's the conversions, percent composition, all of that good stuff. And then you've got some neutralization problems. So you do have all of the stuff we were doing just now. And let's see here. The other one, I can show it to you, but I have to look for it. I'm going to have to post it anyway. And that's the one that is going to be for you. Hold on. I think I'm going to have to go to my Southern one because that's usually where I have, and it's faster. I think, well, let me see if I can find it here, but because it's not responding fast enough. So I'm the kind of person that doesn't like to wait. So documents, I don't want quick access though. No, I want this PC. There we go. And I want the documents here. And I want one thing. See how long it took already? All right, so I want to look for final exam. See, it's not going there. No. That's why I always look, it's easier for me to look somewhere else. Because you would think the final exam would be right here easily. But I want the review. Yeah. I'm going to have to go get it at Southern. This is one of those things. It takes too long. But yours is a little different from theirs, but I can just kind of show you what it looks like. Oh, come on. See, it's taking too long just to log in. That's why I was telling you, it's just like really slow today. But that's the one that I'll be covering. Someday.